I became a ham in 1964, and I joined an amateur radio club outside of New Orleans, and they asked me to teach a radio class for young novices, and Nick was in the class.
Yeah.
So
Okay.
I've known him for since 1964, 65. Anyway, you've all have worked on old boat anchor type radios, and you've probably noticed that when you got to 15 meters and 10 meters, that the power output would go down. Notice that? Yeah, I noticed it too. I have I have many old boat anchor transmitters, and I had 3 or 4 of them on the bench, and I was restoring them. It's more effective to restore them in group than it is one at a time. And I noticed that 15 meters, 10 meters, the power output was down. So I was wondering why. Well, this is a story about that investigation. The Drake T4 series, I like to move around because it helps my knees and it keeps me awake. And also because I taught college for 8 years, I learned that if you follow me with your neck like that, you put little lateral pressure on your carotid artery. And when you do that and you've got it straight on, you have a sudden flow of blood to your head and you don't fall asleep. So that's why. The Drake T4 series of transmitters featured a pair of 6JB6s, 12BY7 driver. And it's the same for the whole production of the T-series Drake transmitters. The only difference is that in the TR3, it used the 12BJ6. Oh, I got that wrong right there. That should be 12JB6. The power output of this combination varies, but with new tubes properly aligned, how many times do we forget those steps? The 2-tube set gives over 100 watts of output power, which is certainly enough to do by itself or drive an amplifier. The issue comes up in the 15 and 10 meter bands. The power output drops off, in some cases significantly. Why? The subject of this paper is to investigate the what and to attempt to find the why. So here are the suspects that we're going to be looking at. The 1967 T4B mated to an R4B to make a TR44B. Anybody ever see one of those? Yeah. Did you ever look at the advertisement of a TR44B? It was made under a U.S. government contract to be used in the Southeast Asia in 1968. You can get on the internet. You know, anything you get on the internet, you're going to believe, right? That's right. The next one is a May 1971 T4B transmitter. And the next one is a T4XC of June 1977. Those are the dates that they were manufactured. All 3 of them were on the bench. All 3 of them are very similar, except, of course, for the T4B, you had to have the R4B because it had a single VFO in the combination. There's the T4B partial transmitter schematic. Let me just point out a couple of things to you. This is the final mixer tube, comes in over through a band switch, and each one of these little trimmers are to be peaked for each of the individual bands, right? All this feeds through that capacitor. You've got a little bridge right there, and that goes into the grid of the driver, and of course, through its own network that goes into the finals. That's typical of all 3 radios. That's the T4B. The T4XB is the same. It's got the trimmer capacitors off the mixer on the grid, into the grid of the 12BY7, and then the tank circuit of the driver into the final tubes. However, it's got this resistor right here. That resistor shows up on the T4B, the T4XB, and the T4XC. And it shows up only on 10 meters. I wonder why it's there. The T4XC, same arrangement, the mixer, the tank circuit of the mixer feeding the driver. But on the mixer output, there is a resistor across the 10 meter and a resistor across the 15 meter. And the resistor that is across the 10 meter on the output of the 12BY7 driver is still there. So if we review, this is what you would call a simplified diagram. There's the last mixer. There's the tank circuit of the last mixer feeding the grid of the driver and the tank circuit of the driver. This little chart tells you R1 does not exist on the T4B or the T4XB, but it's there on the T4XC, and it's a 68K resistor marked R137. Likewise, the same thing with R2 and the same thing with R3. You notice R3 exists on all three of the radios, and that is the resistor that is in the output of the driver. Keep that in mind. The circuitry from the last mixer to the driver tube is generally the same for all three radios. There are, however, changes. The 1977 T4XC, the 15 and 10 meter mixer tank circuits are both modified with added resistors. We have seen that. They act in a shunt. You got power, you got a ground, and you got power, and you got a resistor across it. You got ground, and you got power, and then you got a resistor across it. Sounds like the resistor is going to catch a little power, isn't it? Note for all the radios, there's a shunt resistor in the tank output of the driver stage in the 10 meter position. Now, we do not call the question of a 1960s design intelligence, right? We don't do that. But we wonder why they were there. And sometimes in your fit of heated depression, you say, what the hell is that resistor there for? Because the only thing you see that it's happening is you suspect, I wonder if that has anything to do with the power output of the radio on those two bands. So let's look at some results. This is a little chart. That's the T4B, T4XB, T4XC. This is the frequency in megahertz. This is the driver in volts peak to peak. This is set up with a scope probe. When it's aligned and tuned, it's set up at a scope probe to find the voltage at the grid. And then the stock power output. This is all with new tubes. The power supply is the same. The bias voltage on the radios are all the same at minus 55 volts. And the power supply is the same input voltage at 120. I'm sure that you have used boat anchors that were made for 110 and 115 volts, and you wondered why, gosh, that thing gives off a lot of heat when you plug it into your, in the case of Nick and I, 127 volt main. You notice that for the T4B, 80 meters, 120 watts. Output, 10 meters, 55 watts. All the way down, and you will also notice that the driver in at the grid, you want to go back and look at that? That would be this point right here. That voltage varies as well. As that voltage, naturally, as that voltage varies, so does the output power vary. So that's what we know about what's going on. For the stock equipped radios, the power output tracks, namely the output goes down as the frequency goes up. Look at the driver in the figures. That's those figures on the scope probe. It tracks as well. As you go up in frequency, that voltage goes down. Why the resistor change? There has to be a reason why the T4XC, a resistor was added to the 15 and 10 meter final circuit. And it's just that T4XC. T4B didn't have them. T4XB didn't have them. We don't think, there's a part of me that says, I want to believe that these changes were not just arbitrary. Since the resistor in the driver stage is common, we didn't believe that the vintage of the radio is going to be affected by that placement. So we didn't do anything about the resistor that was in the 10 meter position on the output of the driver. There were obviously a factory change. I had a photograph, it didn't come out too good, of where the resistor was. You almost had to be a surgeon with very good eyesight to be able to even see them. Those resistors showed up unannounced, unheralded, and unnoted, except for the fact that they were there. Why? To help begin to answer the why question, we turn to the FCC for the possible answer. The following is from the 1979 Cumulative Index of Decisions and Reports of the FCC of the United States. If we hams would have written that, it might have taken maybe 3 or 4 words. It says, Section 978.73 amended to require that spurious radiation from all amateur transmitters be reduced or eliminated, regardless of when the transmitters were built or first marketed. So from that point on back to where Galileo was studying moon, we had to change all the transmitters. I don't think that happened. The specific spurious emission standards apply only to transmitters and transceivers built before April 15th, 1977. I often why was April 15th. You caught it. Or first marketed before January 1st of 78, and to all external radio frequency power amplifiers. So, you esteemed fellow hams, you need to go and look at all of your amplifiers and see if the old ones didn't have them, if the new had something, and then you can do a talk for next year. I'll be here. So the resistor changes in the mixer circuit output may be there because of the new order of the FCC. Due to the date, we know that the very early T4B and T4XB have no such resistors in the mixer output. Even though it says, regardless of when the transmitters were built, there was no recall that I know of. We suspect the presence of the resistors reduced the output, but what about the spurious emissions? What was the reason for the addition? That's what we're trying to find out. We're trying to get a handle on the cause of the low power and the reason why those parts were there. Thanks to my best neighbor. Oh, yeah, he is my only neighbor. We used a very neat little spectrum analyzer. This is the T4XC. Now remember, the T4XB, the T4B didn't have those resistors. So I can't do an A and B test on those machines because there is no A and B unless I add a resistor. We aren't going to do that, even though FC's...
Cut the resistor in the ones that you have.
I learned when I was teaching that I had to deal with the audience that I was teaching, which in college means I had to use little words very slowly.
Thank you.
Huh? What's that?
Thank you.
You welcome. So on the T4XC, 20 meters didn't have a resistor, right? So here's a spectrum outlet. That's the fundamental frequency, second harmonic, third harmonic, fourth, fifth, all the way down. You notice that as I go down in harmonics, go up in harmonics, the power output goes down. And you would expect that, right? T4XC on 15 meters without the suspected resistor. This is where in the book they say the plot thickens. The fundamental, look at this little one in here. Where the heck does that come from? And look at this. What is that called? Thank you. That's the harmonic. That's the harmonic. So what about this little bugger right there? Was that what the FCC was talking about, perhaps? Maybe so. All right. This is without the resistor. Through delicate surgery, let's put the thing back in and see what it is. Oh. 15 meters with the mixer in. You noticed that peak is lower than that peak. See it? Oh, no, it's not by much, but it is. So if Mr. FCC asked you, said, yes, sir, we noticed that spur there, and we took steps to eliminate that spur. Little words, very slowly. But you see what happens. There's 15 with the resistor in, without. Okay? You notice also that the harmonics are not appreciably affected as well. Okay, let's go to the next. Same comparison, T4XC, 10 meters without the resistor. And you'll notice, oh, look, I got another one right there. I got a little bitty one right there. I got the harmonic right there. Let's put the resistors in and see. Not much difference, look. Whoop. Whoop, whoop, whoop. A little bit. You see what I'm looking at? Right here. Look at that peak. All right. So there's the evidence. Here's a summary of what that looks like. Again, this is for the T4XC. You've got 20 meters, 15 meters, 10 meters. 20 meters, we didn't see any spurs. There's the harmonic frequencies. This is the output. And with the resistors in and out, obviously there was no change on 20 meters, right? There was no handshaking across the bands. 15 meters. The peak is at 69 dB. The spur was negative 55 down. In the stock machine, that's with the resistors in, but it was only minus 51 dB down with the resistor out. 4 dB. Second harmonic, third harmonic, not much change there. 10 meters, there's the spur, about minus 48 each time. Resistor in, resistor out. Not much change. So we have some evidence that suspects that the resistor was there to comply with the FCC. For the T4XC, the mixer shunt resistor in place in the stock version on the 10 and 15 meter beans caused the spur signal to go from minus 51 on the 15 meter spur to minus 55. That's an improvement. 10 meter tests show little differences in the spur amplitude. So the assumption that the resistors were added to reduce the spurious emissions seems to be correct. The test results show that the resistors did indeed reduce the amplitude of the spurs in 15 meters, but remained essentially unchanged for 10. This tends to prove the reason why Drake added the resistors for 10 and 15 meters and did it generally to reduce the spurious emissions mandated by FCC. Was any of that documented? I don't know. When Drake shut down their operations, I imagine it caused some consternation to the people that were working at Drake at that point. Everything was thrown away. I have never been able, even calling Jeff Covelli, John Kreiner, all of those who used to work for Drake, they don't have anything. Or if they did, they don't say. No data. No data as to what they tested as to the reason why the resistors were there and the effect of putting them there. None. There may be another factor at work here. So here I am, minding my own business in my little shop with these radios bearing their soul to me about these resistors in the T4XC. And I said, you know, that just ain't enough. How are you gonna go through that production change? I mean, not the 10 cents worth of resistors that were in there. It's just changing everything. All of the above measures were taken in the CW mode AGC active. Power output is obtained after tuning by increasing or decreasing the carrier drive. In all of, I'm saying it slow and in little words, in all of the T-series transmitters and transceivers, the control to vary the carrier drive is a common shaft with the mic gain. Everybody know that? Who's got Drakes? Around here you better, right? So in the manual loading procedure of the transmitter, and assuming maximum power is desired, if you had a 100-watt radio, did you use 50 watts? Of course not. Then it's unlikely that the proper value of the mic gain for SSB operation is optimum. You see how that can happen? You're loading the radio up. You're dipping the plate and you're loading the antenna load, and you're going to turn the carrier knob up till you get to the output power. Let's say that you want output power maximum. Every time I did it, I wanted it. So I turned the knob till I got to where the knob wouldn't turn the power up anymore, and I back off a little bit, and that's where I put it. Now, for those rare occasions that I want to run sideband, excuse me, I would plug a microphone into the mic jack, and then what happens if the microphone output was such that it just, I mean, the meter hardly bumped up on AGC, so what would I do? Oh, well, I mean, I just need a little more mic gain, right? What does that do? It overdrives the final stage, and what do you think happened to the crud, the spurious emissions? It went up. How come that the resistors didn't take care of that? Do you think maybe the resistors were, oh, yes, sir. We noticed that in our transmitters. Thank you for pointing that out to us. And we've taken modification steps to prevent that. It's a bridge that might have been sold too. So this could lead to a low gain mic wanting to have its gain increased to the effect of reduction of the output signal quality, made present by more drive than necessary. Likewise, for a hot mic, forgive me, I'm using some sideband terms. For a hot mic, the gain would want to be lowered. And what would happen after that? Your output power would go down. It's not too hard to imagine that when you are loading your transmitter, and then you got it to where you want it, and you plug your microphone in, it's quite likely that the setting of the mic gain is going to be non-optimum for that setting. You agree with that? To add to this reason, for the later versions of the T4XC radio, up to then, the tuning procedure was to tune for maximum power output, varying the gain, which is also the mic gain. That may have led to the spurious emissions that the FCC was concerned about. The addenda says, the tune-up procedure for the T4XC must be altered from the instruction manual in order to meet section 9773 of the FCC. Hey, there's a connection. Tune-up 160, 80, 40, and 20 meters must be altered by limiting the plate current to 340 milliamps. What's the normal procedure current? 380. That's in the book. So you load it to 340 milliamp with the load control. Instead of adjusting the load control to maximum RF out, the load control should be advanced from counterclockwise to the point at which the resident plate current does not exceed 340 milliamps. In other words, you detune it a little bit. The tune-up procedure in the instruction manual may be followed for operation on 10 and 15 meters. Wait a minute. There's no change in the tune-up procedure on 10 and 15 meters? Why not? Because they had the resistors in it. Okay. The new tuning procedure altered the lower frequency bands only. In the T4XC, the lower bands were not changed as far as the mixer circuits were concerned. No added mixer resistors. Note also that in the 10 and 15 meter bands would be tuned as per the book. And we guess it's because the resistors were there, so coupled with the tuning change, everything would have been happy. It's interesting to note another factor that may be in play with the T4 series transmitters. All radios from Drake after the T4 and TR4 units, including the TR5. I have a TR5. What is the TR5? No, the TR5 was actually made after the TR7, and the TR5 is a solid state TR4. No, yes, it's all solid state finals. Yes, it's all solid state. And that means that the TR5 had that same shaft, one control, but dual pots. Could find no data that would suggest this change for any reason other than the obvious mic gain versus carrier gain conflict, coupled with the potential degradation of the quality of the signal. So, is there another procedure that needs to be adopted to prevent that? One possible solution is an extensive modification that changes the dual control single shaft to a dual control dual concentric shaft, just like the TR7 and TR8 radios. If you look at that to see what work that involves, it might be cheaper just to go out and buy another radio. Another could be to use a mic that has an outboard mic gain adjustment so that the radio can be loaded as normal and the mic gain externally adjusted. Anybody have one of those microphones that has the little battery built in that you can adjust the output gain of it? What? Well, yeah, CB microphones had them. D104 had them for a while, right? So what was the setting that you used on that microphone? You grabbed that knob and you turned it until it wouldn't go anymore. Of course. Then again, another way, and I had to put this in here. Another way to avoid the potential mic gain issue would be to use CW. An elegant solution and one practiced by the most discerning hams. I had to do it. But for the T4XC, what about the last issue that began with the drop in power out due to the 15 and 10 meter shunt resistors in the mixer output? The resistor in the 10 meter position of the driver output remained in all the tested radios. The 1977 FCC rule may have been the impetus for some change. We just don't know for sure, but the timing was right. The timing of the FCC ruling and the change of the radios that were manufactured around that time. But what if we just deleted these resistors in the mixer output? If we do, would the power of these two bands increase in line with the lower bands that have no resistors? Let's see. There's our chart again with the last column filled out. This is the modification. You notice that these radios, no resistors, no change. T4XP, no resistors, no change. T4XC, on 15 meters, my power output went from 70 watts to 110. That's pretty good. 10 meters, 75 watts to 100 watts. So our original position is verified. The resistors seemed to be added because of the FCC requirement, but they also had excuse the big word, a profound effect on the output power. We have seen the spectral data shows that when the resistors were removed from the T4XC, the spur amplitude on 15 meters increased. Note also that on the 15 and 10 meter bands, the output power is greater than the stock, which means without the resistors. Note again that the unmodified configuration for the T4XC, the output was down for these bands. Look at the drive. We can go back to that chart and you can see this is the peak-to-peak voltage at the grid of the driver. And you'll notice, for example, T4B, T4XB, 1.2, 55 watts, 2 volts, 70 watts, 2 volts, 75 watts, 2 volts, 100 watts without the resistor. So it did have an effect. In spite of, I'm from Louisiana, right? New Orleans. In spite of one of our illustrious governors, Earl K. Long, you can't get something for nothing. Although he did promise a chicken in every pot. I wonder whether that was ever followed up on. While the research in this issue began with the power output loss in the upper bands, we learned the resistors did reduce the unwanted emissions at the expense of the lower power output. These and the lack of individual control of the carrier and mic levels is a likely underlying reason why the changes were made in the later units. This is one of the many nice results of restoring boat anchor radios. Now, everybody has a different definition of restoration of a boat anchor. My best neighbor, he restores a boat anchor radio to the point where it looks better and operates better than it was when it was new. Okay? I don't do that. I'm older than he is. I don't have that much time. But restoring and making it operate correctly without any compromise is the whole idea. While we have not examined the circuitry of other radios in this time frame, the FCC requirements in 1977 affected all of them. It would be interesting if you have a radio of that era to do a likewise comparison. Take a radio that the production run started before that FCC ruling and then went all the way to beyond the FCC ruling, and just look at the schematics and see if you can notice a difference. It'd be interesting to know. I did not do that. I would like to know if that is in any of these other radios. So if anyone has any such of these issues, gather your forces, use little words, speak slowly, and come back next year and give us a talk. Any questions? Yes, sir.
Yeah, so you mentioned the TR4 incorporated that change. Is that also true for the TR4C and CW?
Yes. Yes. Anything beyond, there's no TR4B.
Right.
It went from the TR4 to the TR4C,
C and CW,
and then CW, and then CWRIT.
yeah. Right,
All right.
right.
Those radios have those resistors. The TR4 does not. Yes, Rob, I was waiting.
Just on a spurious issue, when we got the work bands for 30 meters, you were supposed to use a different crystal frequency in the transmitter, so it tuned 9.7 to 10.2 instead of 10 to 10.5 because of some spurious problem.
Yes, and coupled with that was a modification of the VFO output that changed one of the capacitors from 690 to 400 and something picofarads or something like
You
that.
increased the capacitor almost double, and the output for that high network coming out of the PTO dropped a lot.
Yes.
And it affected the pre-selector peak on 10 meters in particular.
And what did that tell you? It told you that change was, I was thinking last night we ought to make that that capacitor a little bit lower. I think we just ought to just go ahead and do it. That ain't the way it happens.
So it went from 680 to back to
330 or something like that.
390.
Yeah. Drake used the heterodyne oscillator and the VFO were mixed together in a circuit called a premixer. And that's what we're talking about there. It may have been, maybe not totally, but it may have been a contributory to the spurs on the upper bands. I have not checked, Rob, but I can be willing to bet that changed follow through with the later radios. Any other questions? Yes, sir.
Yeah, a lot of times when you reduce power, you reduce your percentage of spurious emissions rather than hitting at max power. And I just wonder if you cut the power back, if you would have reduced it anyhow. Like if you didn't have the resistors and you pulled it back from 110 to 75 watts, would that have been the same thing? And this is just a way of forcing you to cut your power back.
I understand the question, but that really applies only to the accelerator of an automobile. It doesn't apply to ham radio. If you look at a radio and somebody's using it and the gain is at the 10 o'clock position, he's trying to save his radio. So when you tune it up normally, as the book says, it's going to be in a different position. Now, as you vary the output power, you vary these peaks. And they vary mostly in unison. So if you wanted to reduce your output power, you do that. If you wanted to reduce the spur output, you can do that. But can you imagine the effectiveness of a company saying, in order to reduce the spur occurring at such and such frequency, reduce your output power from 100 watts to 33. I wonder how many times that would actually be complied with. Oh, yes. Yeah, I'm sorry. Let me go back to my CW slide. I operated QRP for a while. And then, then my beautiful bride reminded me how old I was, and I cranked it back up and turned the big switch on. Any other questions? This is a good example of some of the satisfaction that you can get from working on old boat anchors. You don't have available, in some cases, like some of the rare Drake radios that I have, there is no documentation. You have the radio, but there's nothing to back it up. There's no instruction manual, there's no schematic, there's no rhyme or reason. You don't even know whether the thing is complete. But when you go into the radios and you try to ferret out a rationale as to why some things were done, you begin to learn a lot about why that radio is operating the way it is. You begin to see, somewhat get into the skull of the designers, and you are able to determine what was their thoughts about what they were doing. So that's a certain amount of satisfaction that you get from doing that. Now, these Drakes are just an example of that. By far, they're not the only example that would be applicable. I would dare to say that every radio has got a little bit of hidden history behind it. And if you're interested, you ought to look for it and come back next year and tell us about it. Any other questions? Thank you much.